Well, welcome to the first of our videos reviewing chemistry for Year 10 Science. In this one, we're going to start having a look at the periodic table. Some of you may find this revision from work that you've done in Year 9 or even Year 8. So let's have a quick look. The learning objectives that we're going for with this video, so just looking at this particular set of objectives from your booklet, okay, is all about the periodic table, the arrangement that the atoms are arranged in for the periodic table, and some trends that we see which are very useful to us as chemists as we start to learn more about chemistry on how to make predictions and know how these elements will behave and the type of molecules or compounds that they will make. So hopefully by the end of this video you are going to be able to describe the structure of atoms in terms of electron shells, and this is something that you should be somewhat familiar with from Year 9, maybe even last year. You may have introduced this and the structure of atoms according to protons, neutrons and electrons. Explain how this electron or electronic structure of the atom determines its position in the periodic table and therefore its properties. And recognize that elements in the same group of the periodic table have similar properties. So we're going to set up the structure of our periodic table and explain how atoms are arranged in that and why it's so useful. So let's get started. So one of the reasons that we study chemistry is because that chemistry allows us to investigate the properties of materials and how they behave. So if we want something that will be strong and flexible for construction, then we would look at something like a metal, like iron, and then we can strengthen that metal by adding in carbon and other things and making alloys for it. So many of the materials that we rely on in society have been able to be developed by a good understanding of chemistry. This includes being able to have the batteries that power your laptops, the special liquid crystals that we use in our laptop screens and our phones. These are all thanks to material science and chemistry. So it really allows us to understand and explain the world around us, including how our body works at an atomic level, so understanding biological processes in that way, and how things interact, being able to understand chemicals in our environment, how medicines work. It's really important for a large number of things. So hopefully you will remember from your previous studies that all matter is made of atoms. The atoms are neutral or uncharged, so they don't have a positive or negative charge when they are what we refer to as their elemental form. So if we're just talking about an atom of, say, sodium, okay, that it doesn't have a charge. Some can form ions, and ions are our charged forms of atoms, but atoms, as we see them listed on the periodic table, are actually uncharged. So this is because they have an equal number of protons and electrons, okay, protons being positively charged, okay, and neutrons being no charge at all but the same mass as a proton, and electrons being negatively charged. So sodium is element number 11, so it has 11 protons. And because it's a neutral atom, it will also have 11 electrons, okay? So inside every atom, there is a different combination of protons, neutrons, and electrons. Neutrons have the same mass as a proton, but they don't influence the charge at all, okay? So they don't have a charge. And then neutral atoms will have the same number of electrons and protons. And electrons don't add to the mass of an atom because they're so tiny. Okay, they're so small they don't have the mass of the electrons doesn't contribute compared to the mass of the protons or the neutrons. All atoms are held together, okay, the nucleus and the electrons are held together by the force of attraction between the electrons and the positive nucleus, okay, and we refer to this as electrostatic attraction. This electrostatic attraction is the attraction between anything that is positive and negative. So because protons are positive and electrons are negative, they are attracted together like the opposite poles of a magnet. So when we write atoms, we write them using what we call nuclide symbol notation, okay, which is this here. This is the very specific way that we write a symbol for an element. Okay, so the atomic number, which is the number of protons in the atom, always goes on the bottom, okay, and it will be the smaller number of the two. And then the mass number, which is the protons plus the neutrons, goes up and on the left-hand side, okay? And then we can work out the mass number. Okay, so for the number of neutrons, these are our neutral ones, we get that by taking the mass number, the one at the top, and then subtracting the proton number, which for carbon is 6 because it's the 6th element, and that means that carbon, in this case, carbon 12, would have 6 neutrons. Okay, so if we have a look at our good old friend sodium again, sodium has an atomic number of 11 and a mass number of 23. Okay, so in this case we can say, okay, so the atomic number is 11, so that's my proton number, is going to be 11. The mass number is the one at the top, so the one at the top is my mass number. So that means if I want to work out the number of neutrons, is going to be equal to the mass number 23 minus the atomic number, which is my number of protons, which is 11, which means that sodium 23 has 12 neutrons. Nice and simple, that one. Okay, and you should have seen that before now. So as we know, every element is different. It has a characteristic atomic number that identifies it. If I change the number of protons, then I am changing the element I am talking about. Okay, so sodium is 11 protons. I cannot have a sodium atom without 11 protons. Okay, so sodium has 11 protons. Every sodium atom will always have 11 protons. As soon as I add one proton, now I have 12 protons. That's no longer sodium, that is going to be magnesium. Okay, so if I change the number of protons, I change the element I'm talking about. Elements of the same type will always have the same number of protons. All carbon elements have 6 protons. All hydrogen has 1 proton. Oxygen will always have 8 protons. Okay, if I change the number of protons, then I change the element I'm talking about. By definition, things with 8 protons are oxygen atoms. Okay, by definition, things with 12 protons are going to be magnesium atoms, and we can't change that. If we change the protons, we change the element. So we've got the protons in our nucleus. Okay, so the nucleus was full of protons. Okay, then outside the nucleus is where we find our electrons. Okay, and we find electrons in what we call shells. These are energy levels. So different electrons in different shells have different amounts of energy. Just like you might have different amounts of energy at different times during the day. You might be sleepy in the morning and have a bit more energy during the day. Electrons have different amounts of energy as well. And they're organized around the nucleus of the atom. The closer to the nucleus they are, the lower the energy. Okay, it's like the closer you are to your bed, okay, you may be sleeping in bed, you're going to be really low energy. You may stumble out of bed to get some food in the morning and you'd still have a little, you're going to be further away, you've got more energy than where you were here, and then if you go out for a run, then you're going to have even more energy, you're going to be further away. Electrons are the same. The closer they are to the nucleus, the lower they are in energy. Okay, so, and the more tightly they're held by that positive charge, pulling them back towards the nucleus. So electrons in the outermost, or what we call the valence shell, okay, have the highest energy. They're the furthest away from the nucleus, and they have the highest energy. So these are the ones that are usually involved in doing something. Okay, they're the ones that will be involved in chemical reactions because they're going to be held less tightly by the nucleus, and they're going to be able to maybe swap and form an ionic bond or do different things. Sort of like you might get up to more the further you are away from a teacher or a parent. Electrons are much the same. They get into trouble, maybe move around a lot more the further they are away from the nucleus. Okay, so electrons in the outermost shell have the highest energy. They have the most potential to do things. The further away from the nucleus the shell is, the more electrons it can hold. Okay, and this is the mathematical formula for how many electrons we can put into a shell. Okay, so n is the number of the shell. If n is equal to 1, then the number of electrons that it can hold is equal to 2 times 1 squared. Okay, 1 squared is 1, so that's going to be 2. So it can only hold 2 electrons in the first shell. Second shell, it's going to be 2 times 2 squared, and 2 squared is 4, so that's going to be 8 electrons. Third shell, 2 times 3 squared. 3 squared is 9, so this is going to be 18 electrons, and so forth. Okay, and this goes all the way up to we can have 7 shells. Okay, so n equals 4, just using that formula again. 2n squared is going to equal 2 times 4 squared. 4 squared is 16, so this is going to be 32 electrons. Okay, so this formula, you should make sure you write in your notes, because that allows us to work out from whatever number the shell is, how many electrons can be held in that shell. Okay, so once we have our number of electrons, we can start to say the pattern that the electrons is in. Okay, and you need to be able to do this up to element 20. Okay, remembering if the element is neutral, the number of electrons is equal to the number of protons. Okay, so in this case, when we write the electron configuration, we write the numbers with a comma between how many electrons are in each shell. When we draw them with the circles and we draw them in. So this means that in shell 1, remember we said it can hold a maximum of 2 electrons. So if I was doing our good old friend sodium, remember it had atomic number 11, so it's going to equal 11 electrons that I need to put. Okay, then the first shell can hold 2, the second shell can hold 8, so I'm at 10, and then I'm out of space in the second shell, so I'm going to put one in the third shell. So 281 would be the electron configuration for sodium. If I was to draw this out, I would put my 11 protons in the middle, showing my nucleus. Then in my first shell, I can have 2 electrons. Okay, and then in the second shell, I can have 1, 2, 3, 4. Now that I've got 4, I'm going to double them up. 5, 6, 7, 8. And then in my third shell, that's a bit badly drawn. In my third shell, I'm going to have 1 on its own. And this one is the valence electron. It's the one that is the furthest away from the nucleus. It's the one with the highest energy. So when we draw them, just as I did before, we make sure this is our friend sodium. We always put 1 electron in each one, and then when we're doing 8, 1, 2, 3, 4, and then double them up. Electrons are drawn in pairs once there are 4 electrons in the shell. Okay, so you should have done all of this work when you did the unit, but if you want to review this, you can review that through doing these workbooks and unit reviews. I'm going to end this video here, and then we will actually cover the periodic table in our next video. Have some practice with your atomic structure and electron configurations. That should all be revision from year 9, but it's okay if you don't remember it. Just make sure you practice it so that the cobwebs get blown away and you are feeling more confident with this. And I'll see you in class.